Swayam Prabha. Digital India. Educated India.
Okay, is understood. Today's topic is reduction in heterocyclic chemistry. All of us know, and I do not have to reiterate that this topic is very vast, but in this class probably in the next class I will just try to summarize and highlight the use of the reducing agents in heterocyclic compounds. Okay, there are by now all of you know there are a large number of reducing agents known in the literature. Just to give an idea about the number of reducing agent in only one particular area, that is boron chemistry. There are more than 50 different reducing agents, starting with boron BH3. BH3 is the simplest one. Then if you put it in THF, that becomes one reagent, THF boron complex. If you put it in dimethyl sulfide, that becomes another complex. Then if you put boron morpholine, that becomes another reagent. So, likewise there are more than 30, 40 or maybe 50 different reagents. Then all of you know the catechol boron, then pinacol boron, then 9-BBN. So, like these, then sec-butyl boron, all these things, then alpine boron. I can tell you some of these names which are widely used. Then so likewise, so if you move from boron to metals, you will find plenty, almost all the metals are reducing agent at somewhere at some point. So, what I have tried to basically collate all the reducing agents under one umbrella in the heterocyclic chemistry, which are more often used or rather extensively used. Okay. And normally there by now there are 4 different kinds of reducing agents in organic chemistry. The first and foremost one, I think all of us know what is it. Hydrogen and metal. Hydrogen, metal supported, metal and a support like palladium, then alumina, all these things, right. And then what could be the second category? Second category could be metal and acid, right, metal acid. Third category could be metal, just simple metal in liquid ammonia, that is the Bart's reduction. And the fourth one, metal and hydrides, and the fifth one metal salts. That is it. So, of you then of course, the sixth one, one can say sixth one is, what is it? Electron reduction. Okay, electron reductions also is quite useful. So, but we will ignore this because in heterocyclic chemistry the sixth one is not often used. And why do you study all these things? There are 2 reasons, or there are 3 reasons I should say. 2 reasons: that you can do a little bit of functional group manipulations, third you can make use of the reduction process to make useful compounds, and third one could be used in the total synthesis or industrial processes. Okay. That means, just to briefly introduce the use of, let us say, reduction in heterocyclic compounds, and how would you make this how do you make this alpha beta unsaturated ketones? Apparently, it looks very trivial, right, because from the very school life you have been studying that this is a process, there is a process called aldol condensation, one can do it, but other than aldol condensation, can you think of any other thing? Okay. I can give you a hint, it comes from a heterocycle, it comes from a heterocycle. Okay. So, the heterocycle could be in fact heterocycle could be, let us say I have to give a try, this is a double bond, double bond, just an olefin, that means you can start from an olefin and then there is a compound, either whether you know or not, this sort of compound, this is cyanide oxide, that means it is a CH3 here, and then you have a triple bond, nitrogen plus, oxygen minus. I think I told you before, it has a name called nickname. What is the nickname? What is the nickname? Quick. Nitrile oxide. So, nitrile oxide cycloaddition is a very useful process actually. This is, and this can be easily obtained from the compounds often we discard in organic chemistry laboratory, oximes. This, if you have aldehyde and then hydroxylamine, you get the corresponding oxime. If you oxidize that with, let us say, sodium hypochlorite, it would produce this nitrile oxide. And then if you react this, and as you can see from this olefin, there is a polarization in this directions and then this. So, eventually it will give you what will give you, you can see it is a process, it is a cycloaddition process, So, also all of you know this process is known as 3+2 cycloaddition reactions. I think probably either in the next class or class after next, we will be talking about the cycloaddition reactions in heterocyclic compounds. This is pretty useful one, very simple, neat and clean, just mix them and the reaction, and often they are reduce selective and also stereo selective often. Okay. Now, you want to make use of this compound, what do you do? Let me see what you can do, you can just, if you think of a selective reduction. When I say selective reductions, means just one of the particular bonds would be reduced, neither this carbon oxygen nor this carbon double bonded oxygen, only the bond that is pretty weak bond, that oxygen nitrogen bond. How do you do so? So, that is what you have to know. Basically, this lecture is on that under particular circumstances, a particular circumstance, you have to use a particular reducing agent. Unless and until you know, then it is you have to just look around all these possible heterocyclic reducing agents. In this case, there are many, quite a few reagents are known in this, but if simple the simple one, I do not remember, it could be either palladium or palladium, nickel or platinum, whichever one of them would be reducing this compound to corresponding imine and then hydroxy, right, and sorry, it should be I think this NH2 and H2, sorry, it should be double bond NH, sorry, double bond NH. Now, if you see, so then if you just hydrolyze, what you will see, what you will get? You will get the one we started with. This is basically as an alternative. There are many uses of this nitrile oxide cycloaddition. What I am trying to say, this is just an introductory slide where you see an heterocycle can be used for synthesizing so called typical aldol type of products and using without using a base, without using an acid to produce this aldol. So, as you have seen already that there are reagents, there are 5 different kinds of the reducing agents. Let us look at the one often used in heterocyclic chemistry, that is basically the zinc HCl, and now we start with a bicyclic heterocyclic system, which is nothing but the indole. Now, let us see what can you do if you react with zinc and HCl, and what is our okay. Between the two, one of these ring would be reduced. Now, you have to make a guess, intelligent guess of course, which one would be produced, which one would be reduced. Any idea? Right, compound is itself is a heterocycle, pyrrole ring, and what is the justification? Higher resonance energy. Very good. So, I think so that means the product would be this. So, benzene has higher resonance energy. So, that means loss of resonance energy during the process is less if the pyrrole ring is hydrogenated. So, and this is also true if you have an isolated case. For example, if you have an isolated case like dimethyl pyrrole. So, you do this same reaction, and in this case of course, the chances are, that means many, but the one that is produced by the way is a partially hydrogenated. It is a 3-pyrrolidine, 3-pyrroline is produced, and then again you have the probability of if this is cis, then of course there are also probability that it can produce the trans one. So, it is a mixture of you get the mixture of the cis and trans. Normally you get the trans of course in more, but in sort of reduction contrary to the hydrogenation. So, you will see a lot of okay. Similarly, I mean I can go on giving you example. The let us say if you have a hydroaromatic systems, means part of it is aromatic, other is not, and then if you do again the same kind of reactions, I think by now you should be able to predict what is the product, that if you have a individual pyrrole ring. So, it is it gives pyrroline, and then you have a 6-membered ring system. That is it. This is a combination of the reduction as well as the so called Clemmensen reaction, that carbonyl is getting reduced to the the CH2 groups. And then probably you are not familiar with some of the things like there are other metals other than zinc. What are the other possible metal normally used in tin? Tin is also used, but heterocyclic chemistry tin I have not come across, because there is a serious problem in tin, actually removal of tin compounds. Most of them most of the time they are insoluble in organic solvent, number one. Number two, I mean if you try to remove that by acidification etc., you get a lot of frothing, lot of insoluble materials. So, tin I have not come across, I mean, but the one that is now user friendly is indium. I do not know whether you know or not. Indium is a nice metal, indium, just indium metal. It is somewhat more stable than aluminum, but also you can use a lot of controlled reduction kind of things. And one of the reduction that has been worked out with indium, let us say you have quinoxazoline, let us say quinoxazoline, and then if you have indium, you do not have to use a very strong acid, just a weak acid, that is ammonium chloride, that would give you the as you can see here the heterocyclic part, that means these pyrazine part would be reduced, and what is basically this tetrahydro compound, and there are plenty of examples. In fact, you also should know that indium is a very mild and reasonably good reducing agent for the reduction of nitro group to the corresponding amino group, and also indium is not that expensive compared to many reducing agents. And maybe I will give you one more example where zinc acetic acid has reduced a nitrogen double bond, nitrogen double bond, and here is an example where you have what is the nucleus. By I think by now all of you know the nucleus I am writing. the nucleus is what is the nucleus, what is the name of this nucleus? Pyridazine. 1 and 2 1 2 nitrogen is pyridazine. So, if you but in this case zinc and acetic acid is the reducing agent. So, it is somewhat mild, but quite interestingly this would give you something like this, which is a ring contracted compound, that is pyrrole. And what is the mechanism? So, the pyrrole is a nice way of making a pyrrole though, and it is a multifunctional pyrrole. So, what do you expect here? The expectation is that as if this nitrogen double bond is reduced now. I mean this is oversimplification, but you can remember in this way that this reaction has been used in many occasions. Then you have this esters here, and then you can guess. So, what could be the I mean you can either use this one or this nitrogen simply in the presence of acetic acid, the ammonia comes out, and what you get is this product, that is it. Okay. And then this compound has been just quickly just review little bit of the pyrrole chemistry here, and if you treat with lithium hydroxide, in the last class I talked about that one of the ester groups should be hydrolyzed, and selectively these pyrrole groups remains intact, O methoxy remains intact, and because of this lone pair effect of this oxygen, this ester is not hydrolyzed. So, this should remain intact, and then this one would be hydrolyzed to carboxylic acid. That is not the this is just an exercise of selective reactivity of the two ester groups, but what I am trying to tell you that this sort of compound undergoes peculiar reactions, unlike normal aromatic compounds. If you react with sodium iodide and iodine, it gives a diiodo compound. I think by now you should be able to work out what diiodo compounds we see, and normally if you want to do the iodination of benzene, just simple iodine is not enough, or even put iron, that is not enough. What you have to do? Right, oxidizing agent, but in this case pyrrole is analogous in reactivity to anilines. So, under the and so with iodine it can give a product which is so rest remain, and that is, and then it gives you the O methoxy here and this. So, this is just a case where that means you can put two different iodines, and with simultaneous loss of the carboxylic acid group. Okay, and you can mechanistically work out, because iodinium mentally you can work out that iodinium ion is formed, then decarboxylation takes place. The first one, this is the first one, that is not a problem at all. Second one, iodination takes place here, and then decarboxylation is the driving force that gives you the this one. Okay, and then there are quickly the next one is, let us say, hydrogen and metal system, and this is widely used. I think chemistry, organic chemistry, reducing agent means the hydrogen and metal. Now, metals could be, all of us know by now, metal could be, the first choice is normally palladium is apportate, then second popular metal is platinum, third platinum oxide, because that is readily available, it gets in situ, gets converted into the platinum metal, and then what else? nickel, fine. Nickel sometimes alone is enough, runny nickel, there is a that is called, it's a runny nickel, right, runny nickel, and then one more ruthenium hydride I have not seen, but rhodium. Rhodium is often, especially in industry, rhodium is somewhat cheaper and plus useful, quite useful. Okay. So, this is runny nickel. Now, in heterocyclic chemistry also all of these are pretty useful, but the trend is little different. For example, if you want to reduce the pyrrole itself by hydrogenation, it is tough. You have to have very high temperature, high pressure, all these things. But if you have an electron withdrawing group, then you can readily reduce it to the corresponding saturated compound. Example is, let us say you have pyrrole, and then okay, the carboxylic ester here on at one side, other side you have a carboxylic ester, and then if you subject it to hydrogenation, the example I have here with the rhodium, and then acetic acid, and as usual this should undergo reduction to the full the saturated heterocycle, that is pyrrolidine derivative, and then corresponding ester. Mind it, the carbon nitrogen bond is not being broken, the ester group is the ester groups are remaining intact. Okay, there is no problem at all. And if you recall the guideline I gave you, that is a very useful guideline. If you have a polar bond, try to use the hydrides etc., polar reagent. If you have a non-polar, carbon carbon double bond, you try to use hydrogen and all these things, this system especially. Okay. And because the reactions are heterogeneous, so they are often stereoselective, and then it gives you the cis 1. And then the next one basically exemplify the similar trend. Here you have the Bock, again a pyrrole, then and see here is a carbonyl, right, it is a carbonyl and an aromatic ring system, and this. Now, the reagent here is hydrogen and platinum and carbon, platinum on carbon. So, what do you expect? So many groups are there, and especially when a group is, let us say is the leaving group is there ortho or para to the carbonyl, they are also likely to be knocked off during the hydrogenations. Okay. Like in this case you have a methoxy here, that is likelihood. You have a carbonyl and you have also amide carbonyl, and then you have the aromatic ring here. What did I say? That if pyrrole is attached to an electron withdrawing group, there is a possibility that the pyrrole ring would be hydrogenated, and the carbonyl is not getting hydrogenated. So, the answer obviously I do not have, I will not write the full structure, you can just write the only part that the changes are taking place is this one, that is it. Okay. That means the pyrrole ring is hydrogenated and the rest of the things remains as it is. Fine. So, we have known. Okay. Let us look at the traditional reduction. Let us say if you want to reduce this quinoline, and you have two different things, benzene ring and this thing, that thing, fine. And the condition, let us say here is hydrogen and nickel and little temperature. So, what would we expect? Which one is susceptible to hydrogenation? Between the two, benzene and the corresponding this pyridine part, because again this aromaticity, the loss of aromaticity is not more here. If you reduce the benzene ring, the aromaticity loss is more. Okay. So, that means the product is here is tetrahydroquinoline 1 2 3 4 tetrahydroquinoline. Now, I just many of you probably know that hydrogenation can also be carried out in the presence of an acid or a base like triethylamine or other base, or even as trifluoroacetic acid, HCl or. Okay. In this example, I give you a conditions where you have hydrogen, platinum and HCl. So, what do you expect? HCl is there, and all of us know the proton transfer reaction is very fast reaction. So, it will immediately pick up or it will be it will not protonate the nitrogen, fine. Now, the hydrogenation would be taking place. So, that means quinoline ring becomes further electron deficient, right. So, what is your prediction? If considering the electron deficiency of the pyridine part, then that should have been reduced, but you have to go back a little bit. As I said, the polarity increases, polarity of the bonds of the pyridine part increases. That means, the immediate intermediate is the protonated one, right, this protonated one. Now, this carbon double bonded nitrogen is now more polar, consequently, its conjugation with the other. So, all these bonds are quite highly polar. So, the reduction product that would be expected now, or rather in fact which formed is this one. Okay, so, that means, just by using acid you can divert the reactions in a different direction, and this is quite in fact this is also very true, let us say very true for the isoquinoline case. Isoquinoline case also the conditions are quite similar. Let us say I give you a condition where hydrogen, platinum and acetic acid, fine. So, what do you expect? I have given you enough of background on the top. Now, this is a isoquinoline case. So, the quinoline pyridine part would be reduced or the benzene ring would be reduced. You can find the analogy on the top. It should be the benzene ring, right, but the answer says it is answer says it is this one. Tell me why. You know the reason. Acetic acid is not that a strong acid to protonate to the nitrogen. Okay. So, if you now protonate with a stronger acid, let us say hydrogen and platinum and then HCl, then of course, the answer would be otherwise. Okay. So, I mean this is just a nice trick actually to switch over. Now, let us look at a case here, little different. Now, we have two different we have two different kinds of the heterocycles. It is a pyridine and this is quaternized, this benzyl group, and then you have OH group. It is a nice example though, nice example. The condition is here hydrogen and platinum oxide, which is known as Adam's catalyst, right. Adam was Adam catalyst, and then trifluoroacetic acid and methanol, let us say. So, what do you expect? Let us say this is a pyridinium ring and a pyridine ring. So, that means, after protonation both the ring becomes electron deficient, both the right, it is a matter of choice. Now, that means, if you protonate this nitrogen lone pair here, that means both becomes the pyridinium, but since you have plenty of trifluoroacetic acid, it can also say that the almost 100% pyridinium ion is formed, and since it is an alkyl group up here, the benzyl, there is a likelihood that the this character of ionic character on the right hand side ring is slightly less, and in fact, in in real life the other ring this remains as it is, and this pyridinium with benzyl group is reduced, and as usual the substituents become cis and substituent becomes cis. Okay. Just maybe one more example. One more example could be, let us say in this case this is a competition between a benzene ring and a furan ring, let us say benzene ring, furan ring, and you have a furfural, and then you have all kinds of methoxy here and there, methoxy and the methoxy. The reaction condition is hydrogen, and the other catalyst is Raney nickel. By now you know, I guess, how is Raney nickel made quickly. It is made from an alloy of aluminum and nickel. Aluminum and nickel, aluminum reacts with sodium hydroxide to get hydrogen, and then it absorbs. Now, I mean, now I think we have enough of examples of these applications of hydrogen in reduction. So, that means you have to keep it in mind whether the polarized, that means polarized bond and aromaticity, these are the two important guidelines. Okay. Whether the bond is getting polarized or the bond is, or the loss of aromaticity is less in the case of the hydrogenation. So, between the two we can quite obviously see, right, between the benzene and furan, the loss should be less in case of furan. So, obvious answer is so obvious answer is, so everything remains as it is, it reduced. So, now you have a mixture of cis and trans though. So, if it is cis, then other also the trans is produced. So, rest remains as it is. Okay. Rest remains as it is. And what next? Other than okay, we will come back maybe I think to other system, but let me quickly go to another kind of, actually sort of hydrogen, but the hydrogens also are quite useful. This is just it is a very complicated example, but this example will tell you many things. For example, I have an example, it is not exactly hydrogen, it is an use of Raney nickel, Okay. So, Raney nickel means it is a nickel, on the top hydrogen is adsorbed on the surface of the metal, and you have now pyridine, pyridine, and then you have a side chain with a double bond, then you have a thiophene ring, I mean so many things. Then you have, right, there are so many lessons actually in this, and TBS all of us know, tertiary butyl silyl, fine, and the reaction condition is Raney nickel and with sodium carbonate. So, what do you expect? Okay. Apparently, nothing is mentioned means it is a sort of a room temperature kind of reaction, reactions. So, that means how many reducible groups are there? The pyridine ring 1, double bond 1, you have thiophene ring system 1, then you have sulfur that can get reduced, then you have cyclopropane. So, so many reducing, but this is very specific, very selective, highly selective. I think in the last year I told you, right, cyclopropane is used for generating in organic synthesis many times. Just quickly, these are the things you have to remember in Carruthers book. Okay. What do you see in Carruthers book? If you do the hydrogenation, what do you get? This is an example taken from Carruthers book. Not really. Gem dimethyl group, which is a typical structural feature of all the terpenoids. So, that means that cyclopropane, and from BSc we have been learning, right, cyclopropane behaves like a double bond. Most of the characters are like the double bonds. Okay. So, that means we have all different kinds, but the product you will get is this. That means pyridine is not reduced under the normal conditions, I means no high temperature, the double bond is reduced, then the thiophene double bond is reduced, both the thiophene double bond is reduced, then this remains as it is TBS and the cyclopropane remains as it is. What else? What I can see that sulfur is nicely desulfurized. This is the beauty. The running nickel is so specific, it can desulfurize. What does it mean? That thiophene nucleus can be utilized to form a aliphatic chain. That is it, and that reduction is very facile reduction. And then of course, a little chemistry, not heterocyclic though. If you almost like room temperature, very quick. We do in our lab also, we often do. No more than 100 degrees centigrade. We did it before a long time in 1994. We just removed S hydrogen and sulfur from an aromatic ring also, Me3. And then this is little chemistry beyond heterocycle. Tetrabutyl ammonium fluoride, all of us know what is the product. Okay. Decellulation. Then you treat this with zinc bromide. Any guess? What should be the product? Okay. So, then OH is produced, basically OH is produced. What next? Actually homoallylic bromide is produced. Homoallylic bromide is produced. Zinc bromide attacks the cyclopropane and this maybe comes out. So, what you will get? You will get this. This is allylic, this is homoallylic. Okay. These are all nice chemistry. So, but all these chemistry could be done because of the selective reductions in this running nickel. I can give you one more example probably. One more example, running nickel such is a nice compound though, it is a nice reducing agent. Let us look at one more example where you have a thiophene nucleus, is a naphthalene moiety and a thiophene nucleus and this. Okay. Here what we use? We use nickel chloride and sodium borohydride. What is it? It is equivalent to, let us see, all these things are taken from Morrison Boyd's Solomon. It is not a very high level chemistry we have been talking about, very low level chemistry. What is it? Nickel boride. The formula is Ni2B. I do not know why Ni2B, but this is the formula given by all the books. This is known as nickel boride. It is somewhat equivalent to runny nickel. And so, obviously, the answer of this reaction, the product of this reaction is this. So, ethyl benzene. So, nice reaction. I have more examples if the time permits, we will talk about it. Next, let me maybe we will give you one more example. This also tells you many things. Again a thiophene, and then you have the carbamate side chain, again a carbamate side chain, then you have a side chain up here with a carboxylic acid. Do not worry about the number of the carbons of the chain. Now, the reaction condition is hydrogen and palladium carbon, and the solvent is acetic acid, and whatever the reaction product is excellent yield, 95%. So, what do we expect? This is basically this is our job. We have to gather some knowledge, you have to extrapolate some knowledge, and you have to predict something. So, we have so many reducible groups. You have a carbonyl up here, you have a carbonyl up here, you have a carbon sulfur bond, you have a carbon double bond nitrogen, you have a carboxylic acid. So, all of us know hydrogen is not suited for the functional group transformations like carboxylic acid, amides, etc., and possibly double bond and this thing. and many of you already know that this palladium often gets poisoned by sulfur, quinoline, etc. So, you have a sulfur here, that means sulfur is not knocked by the palladium catalysts, but it can assist the hydrogenation. That is the difference. Raney nickel can knock off the sulfur, but this one, that means the product that would be formed here is this, and so so all the hydrogens are cis now, added hydrogens are cis, and the rest remaining as it is. So, when I write bracket means rest of the things are as it is. Okay. So, sulfur is not knocked out because of, by use of palladium. Okay. What next? Next is very important next. What next? Bartz reduction. Bartz reductions you have learned, it is a very useful reaction, very useful reactions. In fact, for a long time this reaction was not used in heterocyclic chemistry. Very few scientists actually made use of this. One of the person who used is, I think I will tell you the name, don't know how, from Cambridge, he is still using this reaction. Heterocyclic chemistry it was not that prevalent, and but all of us know. Let us begin with the simple one, or one of the latest examples of Bartz reductions of the heterocyclic molecules. A pyridine nucleus with the carbonyl up here, then 4, 5, 6, 7 membered ring, and then you have a 5 membered ring. So, you can see that you have a pyridine nucleus, and there is on the middle you have, what is the name of this nucleus? By now you should be able to know. The middle ring should be named as, quick. The middle ring, what should be the name? Oxazepinone, 7 membered ring oxazepinone. Okay. The metals in by Bartz reduction, normally Bartz reduction metal sodium or lithium, and okay, very occasionally people have used calcium. I mean Bengtsecker at Purdue University used that. Let us see, so lithium, sodium and liquid ammonia. Liquid ammonia is a solvent, of course, and then what do you use? Allyl bromide. I think all of us know the reason. What is the basic background? The basic background is that if you have a benzene, Bartz reduction is a process, it is a dearomatization process. That means the double bond should, that means what you will get? You will get this one, cyclohexane 1,4-diene, right, 1, 2, 3, 4, cyclohexane 1,4-diene. Okay, this is deconjugate process. In fact, very recently one paper has come out in Orglet. They have done sort of a Diels-Alder kind of reactions, the diene and a triple bond, and in the presence of an organometallics they have produced this 1,4-diene system. Any case, but if you know the mechanism, this is single electron transfer, it goes through radical anion, then eventually it goes to anion, and then the reactions also is coincident with tertiary butanol, then the proton is abstracted. So, the product is formed. So, this you have to mind, and what is the driving force for the reactions? The carbon anion stability. So, if you know this basic mechanism, then you should be able to predict what is the intermediate. The intermediate should be and anion should be here, that is alpha to the carbonyl, and if that is so, then the product of course, you can guess whether the product would be allyl would be incorporated in the anionic center, and the rest as it is, and this was actually published by Ganesh Pandey of NCL this year, last year. Okay. So, likewise that Cambridge scientists have made use of the reduction again of these pyrrole unit. So, you can guess what should be the okay. So, here what is the requisition what is the requirement? The requirement is that you have to have an electron drawing group, because that makes it a little electron sink, and then the normal catalyst or reagent, that is lithium and liquid ammonia, and then if you have R x, now you can guess. So, you know that the mechanism actually leads to a carbon ion, and now carbon ion is stable at adjacent to the carboxylic ester group, and so that is, if that is so, that means and the bulk is this amide basically. So, that means what you will see anion would be this, at the ester alpha to the ester, and this is ester here, and the product of course, as usual the product would be this R here, then ester here. So, what you get is a pyrroline, means dihydropyrrole. The same thing, similar, I mean this is exactly, I mean it is applicable also, this is applicable also to the furan compounds. To the furan compounds also you will get this furan up here and this R, and in this case the example that I have seen that with amide. So, that means what it means, that pyridine, pyrrole, furan, all the 3 nuclei, if they are electron deficient, can be reduced by Bart's reduction to the partially hydrogenated products, and I have one more example, probably I think I will come back a little later maybe. This is typical the same example, and then one more, I think I will give you one more example maybe from Bart's reduction. This is let us say now there is a little change. For example, suppose you have a substrate where ester is at 3 position, and then you have a protecting group called ADCO. So, ADOC. Now, you do the Bart's reduction, and then and Rx. Okay, what? Right. AD means AD stands for actually adamantile and adamantyl oxycarbonyl. So, now the question is the product, whether the Bart's reduction intermediate would be like this or what? Or what? Or well, truly speaking, I mean this is not de-aromatized. I mean this can be equivalent to somewhat de-aromatized. Not only that, it is alpha to the ester group, So, in this case, this is a special case, in this case this one is formed, and then of course, when you have Rx, so this nitrogen is not alkylated because you have this amide group here, ad hoc means amide group. So, you have this ester group here and the R is attached to the alpha to the region is only that ester is getting stabilized with the the carbon is stabilized by the ester. De-aromatized, see in this case it is not de-aromatized, it can undergo further reaction. That means, had the reaction taken place, however this is conjugated to the ester group. For example, many of you know, if you want to reduce this to the saturated one, the quickest way is to, or the very convincing way is to use lithium and liquid ammonia, because Schwarz reduction is not only used for the dearomatization of the aromatic systems, you can also, that is why Schwarz reduction is defined as deconjugation. This conjugation is broken. Had this been found, this had given the fully aromatic system, fully dearomatized or fully saturated system. Okay, that is one of the, I mean, since I know the answer, so I can argue that okay, probably because the carbon is stabilized by the ester. So, this is likely to be for, plus it is tested by the alkylation study. Alkyl group enters the alpha position, and so I mean, then let us say there is an example also I can give you. Let us say this is a kind of Schwarz reduction elsewhere also has been used. This is a case from the terpene chemistry. You have an alpha beta unsaturated system and like this, and if you have this reaction with hydroxylamine. So, all of us know what would form, it would form the corresponding oxime, right. Okay, oxime should have normal trans, but in any case I will write trans, I use that. Then if you treat this with iodine, actually it forms iso-oxazolene, fine, iso-oxazolenes, and you have a double bond, you have cyclohexane ring system and this thing, fine. Now we have generated basically new heterocycles, iso-oxazole, and if you want to reduce this selectively, this one, what reducing agent would you use? What reducing agent? You have a carbon double bond. So, this situation is different. Okay. Normally metal acids, zinc acetic acid, etc., very useful. Okay. But but in this case sodium and liquid ammonia has been used. So, what you will find, that means this one is selectively reduced and selectively reduced, and so this is OH. Then what? Then tautomerized, but mind it, stabilization is so powerful, is a driving force, it can knock off the amine group. So, result is everything remains as it is, and you have a carbonyl up here, double bond, and this. If you compare this one, right, what is it? What do you see? What is the transformation? Isomer. So, it is an isomerization. The best way to this is a synthetic, this is called transposition, means you just exchange the positions, that is called transpositions. Like one of the papers in literature you will find, this is a case I think this is one of the course I often like it, because this is from my area. Okay. And I think I told you before, this is called transposition. The methylene has been exchanged with the CO group. This is called 1-2 transposition. This is called 1-3 transposition, 1-2-3. There are quite a few review articles. And let me give you one more maybe example. Let us say this is the last case, metal hydride. We have not talked about the metal hydrides, right. So, that means what you need is a polar bond. If you let us say pyridine and alkyl group up here, and then you have side chain, then you react, you want to, let us say you want to get to the compound something like this, sorry. So, partial reduction, here you have the carbocation here. So, what reagent would you choose? We have 5 different categories: hydrogen, palladium, just simple, then hydrogen metal, and low valence metal salts, and then the hydrides. Okay. And obvious choice is here is a polarized bonds. So, with the metal hydrides, and this is nothing but simple sodium borohydride. Sodium borohydride would reduce this to tetrahydropyridine. Okay. And maybe quickly I will give you just last example. You have to tell me the answer next class. Okay. This is from a no, next class means after midsem, fine. This is little bit of from the silicon chemistry. Let us see. I think you have learned silicon chemistry from Carruthers book. Is a very good book. There are plenty of silicon chemistry there. If you treat this with lithium and then excess trimethyl silyl chloride, then you give, okay, maybe some fluoride is possibly some fluoride, possibly I do not know, assume that there is a fluoride, and furfural, is the electrophile, fine. This is one example, this is one homework, it is not included in the exam though. So, you suggest a suitable product that will comply with this reaction set. Maybe I will give you one more. Okay. I think this one we can do it now. Let us say how can we convert this to this. I have many more examples though, because it is a versed course. Okay. Basically, what I said, there are 5 different kinds of the reagents. One is the hydrogen metal, one is these metal acids, then metal liquid ammonia, metal hydrides, and metal salts. Metal salts means normally I say nickel borate I said, and then sodium borohydride, or sometimes lithium aluminum hydride. Occasionally there is a new reagent also, many of you know, called samarium iodide. Samarium iodide also occasionally is used. Okay. Any idea? Let us say how do you do? Let us say the last one, for example. I mean, what is the example for? Example for the illustration of? Right. So, Raney nickel, what does it do? It knocks off the sulfur as well as removes the double bond. That means you get a saturated systems. Now, if you do the electrophilic substitution reactions on the thiophene unit, so you can get the introduction of groups here, because these 2 positions are blocked. So, if you do the electrophilic substitution reaction, 3 positions would be occupied, and then do all kinds of requisite transformations, and then eventually you do use Raney nickel, because Raney nickel is very specific for sulfur and double bond, and it will not touch the carboxylic acid. Okay. So, this is a case of when I say lithium and TMS chloride, what is the case? This lithium and trimethyl silyl chloride. What is the reaction? Okay, it is again a Barset reaction case, but okay, I will give you the hint. I think then that would be useful. Actually, all of us know Barset reaction goes through anion, but in this case 2 silicons are incorporated. This is the intermediate. How is that? Okay, disilylated dihydropyridine. So, now suggest what is the next product. It is a combination of 2 different reactions. Okay. So, but